presentation. I'll now go to Mr. Pritam Jyoti Borah, Center for Atmosphere and Ocean Sciences, Institute of Sciences and Devicha Center for Climate Change, IISc Bangalore. His talk is on North Atlantic influence on subseasonal variability of Indian summer monsoon rainfall.
Hello, can you hear me? Hello?
Yeah, we can hear you.
Yes. Hello, everyone. Today I'm going to talk about my part of my PhD work, where we have looked at how the mid-latitude influence in causing subseasonal deficit in Indian monsoon droughts. So this is the work with Professor Venugopal and at Indian Institute of Science. So, all right. So in the first part, I will show some precipitational analysis to look at the rainfall variability of Indian monsoon droughts. And the second part, I will show some key results from our dynamical analysis and possible factors that influencing that rainfall variability in Indian monsoon droughts. So let's get into it. So if you see the interval variation of Indian summer monsoon rainfall from this IITM picture, what we see is that since 1901, we have about 23 drought years over India. I mean, over the main homogeneous region. And among them, nearly 50 to 60% of them happen in presence of an El Nino. So that means nearly 50% of them didn't happen when happen in absence of an El Nino. So there are about like 10 drought years in which happen in absence of any tropical equatorial Pacific forcing. So we focus in the second category of drought years, this non-El Nino drought years per se. So why is there any large-scale pattern associated with it? So we have primarily used a data set from IMD daily rainfall data set. Then we have also looked at South Asian region using Aphrodite data set. Then for large scale circulation patterns, we have used IISc, and for ERA daily global reanalysis data set for dynamical analysis. So if we see the large scale SST picture for these two categories, for El Nino droughts, we see an expected strong El Nino signal. This is expected with Central Pacific signature to it. And for non-El Nino droughts, which is of our interest, we see equatorial Pacific is near-neutral. But interestingly, what we see a strong cold SST anomaly over the North Atlantic region. So this is the first large-scale pattern we associate with the non-El Nino droughts. So we'll come back to it later. So these are the years I have highlighted for these two categories of droughts, which are occurring at across the different years in the last century. So let's come back to the rainfall. So if we take these two categories of droughts, and if we plot the daily rain distribution on a seasonal scale, that is, these are daily rainfall anomaly, and if you take for the whole season, what we see is that they are significantly different from the mean normal rainfall distribution, which is expected, shown in the gray bar. But in between these two categories, El Nino drought and non-El Nino drought, statistically, they are indistinguishable to one another at seasonal scale. So when you look at from the seasonal perspective, they both look identical. So there's no way to at 5% significant level. So what we next did to look at these drought years in a finer detail, we look at the daily anomalies of each of the years. So in the first category, we show the daily rainfall anomalies of each of these years for El Nino drought years. Then the second category are the non-El Nino drought years. So from the first observation, what we see is that these strong blue periods that are basically the break periods that are happening. So for El Nino droughts, most of the breaks are happening during the peak monsoon period when we receive the most of the rain, that is July and early August period. And on the contrary, the non-El Nino droughts, most of the break periods are happening, that is the strong blue periods are happening in the later part of the season, not in the peak monsoon period, and it continues through the September. So if you take a composite of the two categories, what we get it to daily anomaly curves. So in the thick curves are basically the first three harmonics. So what we see is that the red curve, that is the El Nino droughts, it stays overall below normal for the whole season. And the non-El Nino droughts, what we see is that during the peak monsoon time, that is July and early August, you see a kind of normal monsoon behavior. You see also a revival, but then there is a dramatic decline in the late August, and deficit remains below normal. So to see it clearly, what we did, we plotted a cumulative anomalies of the daily rainfall. So what we see For red curve, that is the El Nino droughts, you see a gradual decline throughout the season. So that is the characteristic of a seasonal deficit. On the contrary, for a non-El Nino droughts, you see a moderate decline in June, but during the peak monsoon period, it remains flat. That is, it's having a normal monsoon behavior. But this abrupt deficit in the late August, which brings down the anomaly towards a drought kind of condition. So this non-El Nino droughts is showing a subseasonal kind of deficit. So if you see this 1 sigma deviation of these two drought cases, what we see in this picture. So in El Nino droughts, up until mid-August, it behaving still remaining in the periphery of a normal monsoon behavior, but this dramatic decline in the later August makes this season a drought year. So something particular about this abrupt decline we should focus on, and what causes this drought. So we have these are the 20-day accumulation anomalies of our spatial distribution of rainfall. So for El Nino droughts, we see the most of the deficit is coming from the late peak season, that is July and August. And for non-El Nino droughts, you see during the peak monsoon time, you are having a normal monsoon, but then there is a sudden dramatic decline in the later August, which makes these drought years. So what's happening in the regional monsoon while we are having this India is experiencing drought. So we have looked at aphrodite data set. So we plotted the same 20-day accumulation of anomalies. So they are, first observation is they are consistent with for El Nino droughts, we see a peak season decline, then it continues throughout the season. And for non-El Nino droughts, during the peak monsoon period, there's a normal monsoon, then this sudden abrupt decline in the later part of the season. So now let's look at the global reanalysis product to see the possible global factors responsible for it. So and the second observation is that when India was having this drought, that maritime continent, you see a normal monsoon. So something particular about this deficit that is very localized over India. So which prompts us to go back to our SST anomaly, which we observe, to see if there's a mid-latitude role to it. So these are the moisture availability during this non-El Nino drought years. So we have plotted here the moisture flux divergence. So you see clearly in the later part of the season, you see a very positive divergence over India. So which corresponds to this abrupt decline in the late August. So this basically means we have a reanalysis data product on a composite scale. It's go hand in hand with IMD rainfall. And now let's go back to the SST anomaly we have observed over North Atlantic region. So what we see is a cold SST anomaly. So if we plot the upper level atmosphere over this North Atlantic region, what we see is a strong cyclonic circulation over North Atlantic region on a seasonal scale, and it's stronger. So this basically means, and the shading is a vorticity anomaly. So you see a strong deep tropospheric vorticity forcing generation over the North Atlantic region. And this is again a seasonal scale, but I will show you that it actually has a subseasonal evolution pattern. So if we focus on the abrupt decline part of the monsoon, that is August 20 to September 8. So if we plot if you see the large scale structure of wind anomalies for the first 10 days of the deficit, what we see is a cyclonic circulation that is we have seen it present throughout the North Atlantic region, and which triggers a Rossby wave train. And it's subgeostrophic to the northwest of India, and it leads to anticyclonic circulation over at lower level, and which suppresses the monsoon flow in terms of the, you can see in the negative vorticity anomalies at lower level, and it leads to rainfall suppression for next 20 days at least. So this Rossby wave train coming from the North Atlantic is responsible for this abrupt decline we see, which is very atypical of a monsoon variability. So if we just focus on this, what's special about this North Atlantic vorticity forcing, what we next did, we take this SST anomalies of the North Atlantic region on interanimal scale. Let's see the warm periods and take the cold periods in green, and construct the vorticity anomalies throughout the season from June to September for these 2 periods. So what we see is that going beyond drought years, these cold SST years are having a subseasonal vorticity evolution in the early part of the season and the later season. And interestingly, the opposite is true for the warm periods. So, and if you see the blue curve, that is the non-El Nino droughts, you can see the vorticity generation in the later part of the season is significantly stronger. So where you saw that wave train coming in, and we are having an abrupt decline in the later part of the season. So this basically shows the association of the interseasonal vorticity generation of our North Atlantic region and rainfall depression suppression over India. But again, when we are looking at non-El Nino droughts, so when we are generally looking at years where the Pacific is near neutral, near normal. So in summary, so from precipitation analysis, hello. Yeah. So in summary, so in precipitation analysis, we have seen a seasonal deficit in non-El Nino droughts where, for non-El Nino droughts is caused by a late season decline, which is basically a subseasonal deficit. And we first see an North Atlantic cold SST anomaly. And from dynamical analysis, we have observed that a Rossby wave train, which is coming from the North Atlantic, is causing this abrupt decline. And this wave train is associated with an episodic vorticity generation that is have a subseasonal evolution to it. It's not a stationary pattern, but it has a subseasonal nature to it. And which is true for not just only non-El Nino drought years, but generally cold SST years as well. So just before ending my presentation, I just want to show a evolution of daily rainfall anomalies for these two category of droughts. So if you just see, starting from June 1, you can see these two category of droughts, the negative and rainfall deficit is building up. So by the end of June, so you can see a moderate deficit in both the cases. No, there is no difference to it. But as we move to the peak monsoon period, we can see for El Nino drought years, the break condition is already set up. It's a widespread deficit, and it's about like mid-August, and you can see for non-El Nino drought, it's still hovering around normal or below normal. It is still the break is not gonna hasn't happened yet, so we don't know where to know is it going to happen. But suddenly, so the next 20 days, you can see then the break condition has happened over homogeneous core monsoon region. And as you go towards the end of the season, you can see on a seasonal scale, basically, the drought category look very identical to one another, which we again see in the seasonal our distribution rainfall. So it's the subseasonal nature of this non-El Nino droughts which makes them different from the El Nino drought years. So with this, I will end my talk. Yeah, thank you.
Thank you, Pritam. It's a nice talk, especially the two distinct droughts that you brought in. If any question is there from audience participants, please.
Yeah, Mr. Pritam Jyoti, it's a good presentation.
Hi, hello.
You actually mentioned about the non-El Nino and the drought combinations, where you have this cold SST anomalies, which is persistent over the North Atlantic region, right?
Right.
And this North Atlantic vorticity forcing, actually, when you analyzed,
yeah.
And have you made a comparison with the normal years, non-drought years?
No. So yeah. So actually, I haven't shown here that part. So there are like years where SST was cold, but we didn't have a drought year. So it is not always true that we understand. So that was my next part of the work.
Because so I'm trying to understand the teleconnection between these actually.
Yeah. So actually, you're correct. So not all the cold SST years is leading to deficit over India. That is true. So that was our second part of my work. So I haven't shown here that part. That you are correct. So
and also you mentioned about this abrupt decline that is happening after the month of August. Yeah, so is it seen for all the data being analyzed, or for a particular year only it is being seen?
So this is composite analysis. So it is true for a general overall category of all the droughts.
Okay. And this composite what you made for the El Nino and the non-El Nino is, I think you are referring to the first harmonics, right? The figure that you have shown is for the first harmonics. This one, yeah.
Yeah. So I just first three harmonics basically.
First three, okay.
First three harmonics. So just to show the large scale pattern, but you can. It is also evident from XWell daily values as well.
Okay. Thank you, Pritam Jyoti.
Yeah. Thanks. Thank you.
Yeah, Pritam, just one question.
Dr. Rajkumar.
Yeah, Pritam. Whether you analyzed any this regional drought also, regional scale pattern also, means within India itself, because when I see your slide for the El Nino versus non-El Nino, West Coast side is always since beginning itself is like that. even both the cases.
Right. So you mean that western coast in both the cases, right? So
yeah, not western coast, whole west, if you see.
Yeah. So we haven't looked at in regional scale how it is developing, but the idea is that like earlier studies with give that how the cold air as it enters over toward the northern India, it basically dilutes the temperature gradient, and it basically weakens the monsoon flow. I think that in both the cases the western coast also looks very negative. So I think that could be the manifestation of it. We suspect. So I'm just speculating it at this point. So by the weakening of monsoon flow, it leading to that overall deficit in both central India and the western part. So but I may have to look at more detail.
That's because normally we are facing the problem with the prediction of the breakaways. So if anything can be done, using such thing for the breakaways, that will be very, very useful if we can do.
Right. So I think one question it poses about this non-El Nino drought. So sitting in May, can you predict that abrupt decline? Is it going to happen or not? So that is one poses a question from the predictability point of view. But I think there is always that problem remains that because we are looking at seasonal extremes, so we do not have a lot of samples. We have only like 23 drought years. So you have to be also careful with how you interpret and analyze. So
okay.
Thanks.
Thank you, Mr. Pritam. Now I'll go to the next speaker, Dr. Sudarshan Bera, IIT Pune.
Kusuma Madam has a question. Dr. Kusuma Rao has a question.
Yeah, please.
Sorry, I could not raise my hand there. Some problem. Did you look at these raspberry trains? Raspberry waves.
Right. Yeah.
During the El Nino year, the drought years.
During you mean El Nino years? So we the dynamic analysis we have only performed for non-El Nino years.
Non-El Nino. Oh,
yeah.
okay.
So El Nino years, because like to attribute the deficit to the Rossby wave train, because there are always inter-hemisphere inter-basin teleconnections and all those things. So we let's just focus on the non-El Nino part. So yeah, I think that part we haven't.
Yeah, special is Raspberry wave trains, is it the phase locking occurring?
Yeah, so it's basically a episodic nature. So it just come for like 10 to 20 days, about 10 to 20 days. So it basically the subgeostrophic part as it enters over the northwest part of India, it just causes a deficit for next couple of weeks and it goes away. So phase locking could be one part, that is true. So I think one of the ways to look at also the presence of the Tibetan plateau as it remains over the northeastern pipe, because it also helps create squeeze that Rossby wave train towards India. So it is also evident at 500 hectopascal.
Yeah, because these raspberries are there always. So
yeah,
what's special during the non-El Nino years? That is maybe phase locking, I was thinking.
Right. So I think that is so that's why we found that the association with the vorticity forcing. So if there is vorticity forcing, it can lead to such kind of Rossby wave train. So that is the association we found. So I'm not saying a causality, but an association in like cautious terms.
Yeah.
So yeah.
Okay. Thank you.
Thanks, ma'am.